Hi, my name is Cooper Stone, and this is my Physics 2212 lab about lines of charge. So in the previous lab, we assumed that charge was distributed as a point charge between two pieces of tape, and then by making the top one float and measuring the distance between the two and setting the electric force equal to the gravitational force, we found the assumed charge of that piece of tape. This model is different in that we will be assuming the charge is evenly distributed across the tape as opposed to a point charge, which is a more accurate representation based on polarization. And the model showed that there is a positive charge of the tape of 2.699 times 10 to the negative 8 coulombs. So a couple of essential concepts. Gravity on Earth's surface, the force of gravity is equal to an object's mass times acceleration due to gravity, or 9.8 meters per second per second. And Newton's second law states that change in momentum divided by change in time on an object is equal to the net force acting on that object. We also use the electric field and force equations, the electric field equation being Coulomb's constant times the charge that's creating the electric field divided by the square of the distance between the observation point and that point charge that's creating it. And to find the electric force, simply multiply that value by the charge of whatever the original object is acting on. One new concept in this lab is the idea of superposition, which states that the net electric field acting on an object is equal to the sum of all the electric fields acting on it. And it's also assumed that these electric fields don't interact with one another, so they don't take away from one another. And in this case, this is important because we're assuming the sum of infinitesimal charges dq all work together to create that net electric force that acts against gravity. So they each have their own electric field that don't interact with one another, but summing them all up will find the net electric field of that tape. Some assumptions is the same. The experimental assumptions are the same as in lab 1, such as like negligibility of air resistance and loss of charge, and then equal magnitude charge. But the main difference is that here we're assuming that the tapes have charge evenly distributed across their surface, as opposed to just centered right in the middle of them. So the experimental results will be used from lab 1. So there's only coding methods involved in lab 2. And in this case, we're creating a model to simulate that even distribution of charge. And then based on the electric force it calculates, finding the charge of the tape that would provide that amount of force. So simple kind of model showing the system. Top tape has a net force of 0 due to gravity and electric force canceling each other out. And we are finding what charge required if the bottom tape would allow for that to happen. So from lab 1, the distance between the tapes was 0.0294 meters, and the computational model for point charge found that the tape had a charge of 1.348 times 10 negative 8 coulombs, a positive charge. In my model, you can see on the left I define physical constants and add the results of lab 1, and then on the right I actually create the function for a line of charge, modeling that, as well as creating a function for the electric field, just to kind of solve that. Here I also found the electric field and the electric force, and modeled that as seen here with various errors. And then here I used I found the net electric force and gravitational force before expressing them, and then using that value to determine the new charge of the tape. So on the left you can see the lab 1 results, and they're modeled as point charges. And on the right, you can see lab 2 results where multiple arrows from multiple sums dq all acting together to create that net electric force. In lab 1, the charge was found to be 1.348 times 10 negative 8 coulombs, but in lab 2, it was found to be about 2.699 times 10 negative 8 coulombs, almost exactly double of lab 1. And in this case, a higher magnitude of charge makes sense, because in lab 1, the point charge, all of the electric force was going straight upwards. But in lab 2, because that charge was distributed across the tape, some of that force has a horizontal component. So in order for the y component to have the same magnitude as in lab 1, there has to be a higher charge so that it can contribute more to that. And then some sources of error include the error involved in lab 1 results, and then scaling values in this computational model, which I did as I saw fit. One question is, what if you had modeled each of the tapes as a single point charge, like in the previous lab, and then how would that impact the comparison between the two? Like I said, the charge was almost exactly double in lab 2 as a result, because there's horizontal components that were not accounted for in lab 1, the point charge model. And they differ because, like I previously said, the line charges have horizontal components that cancel each other out, but even though they cancel each other out, they still take away from the net force that it creates. So for it to have the exact same vertical component, it must have a higher charge because part of it is being taken away by the horizontal components. And this is more accurate because charge spreads out more evenly through an insulator due to polarization.